This webcast discusses the concept of work. Work is a way of transferring energy into or out of a system because of an external force. And so two things occur whenever working is done on a system. There has to be a force that's applied by an external system, and also something within the system that you're looking at has to move. If the force does not cause some type of movement, then there has been no work. So if there's no displacement, no work has occurred. So think as this simple example, someone trying to push a very heavy box, and she huffs and she pushes. She's really pushing the box, but the box does not move. So she has applied a force to the box, but the energy of the box has not changed. It's still at rest on the ground. And so a physicist would say that she's done zero work. She has applied a force and she has caused some of her energy to dissipate, I suppose, but she has not transferred energy to the box and given it an additional amount of energy. So work is the transfer of energy by some external system applying a force parallel to the direction of motion. Only the component of the net force that is parallel to the displacement actually transfers energy. So in this example, a woman in a warehouse is pushing a crate and she's applying a horizontal force. That horizontal force is in the same direction that the crate is moving. So all of her force is transferring energy, and the work, which is the energy transferred, equals the force multiplied by the displacement. So the force that she's applying on the box multiplied by the displacement of the box. Here's a different example where the woman is pulling the box in the warehouse, but she's pulling at an angle. And so if we resolve the force that she's pulling with into its horizontal and vertical components, only the x component of that force is actually parallel to the direction of motion of the box. And so that is the only component of force that is actually transferring energy or doing work. So here the work equals that x component of the force multiplied by the displacement of the box. The y component of the force is perpendicular to the displacement of the box, so that y component is not doing any work. It is not transferring any energy into the box itself. Work is a scalar quantity, meaning that it has a magnitude or an amount, but it does not have a direction associated with it. And the unit for work is a joule, which is the same as the unit for measuring energy. Let's go work a few problems involving the work. So I'm going to go to worksheet 6G, and let's see. So as we're starting out here, number one, we have a situation where Charlie is pulling horizontally to the right on a wagon with a force of 37.2 newtons. So here's an applied force on the wagon by Charlie. 37.2 newtons. Sarah is pulling horizontally to the left. And she's applying a force of 22.4 newtons. And we'd like to know how much work is done on the wagon after it has moved 2.5 meters to the right. So here, the net force is going to be the 37.2 minus the 22.4. The wagon is moving horizontally, and so we care about the net force in the horizontal direction. So there's a net force of 14.8 newtons. That's to the right. Right, there's more force pulling the wagon to the right than there is to the left. The displacement of the wagon is 2.5 meters. the work is going to equal that net force times the displacement. And so it's going to be 14.8 newtons times that 2.5 meters, which is 37 joules. So Charlie and Sarah together are transferring 37 joules of energy into the system with the wagon. Let's think of another example. So here we've got someone and they're pulling a suitcase through the airport, I guess, with a force of 25 newtons, and the handle makes an angle of 36.5 degrees with the horizontal. Okay, so if we were to do a little force diagram for this, here is the applied force on the suitcase by the pilot, and that is 100 newtons, but we're really interested in the x component here of that force, because that's the component of the force that is parallel to the displacement. This angle is 36.5, and so Fx is that 100 newtons times the cosine of 36.5. Which is 80.39 newtons. And if we're looking for the work is that component of the force that's parallel to the displacement times the delta x. And so that's the 80.39 newtons times the 10 meters, which is 803.9 joules. Okay. Let's consider a couple of other examples. These first two are simple, but they illustrate an important concept. So we have a cat pushing a little toy ball. It's just a 25-gram ball, a very light one, and it causes it to go from rest to a speed of 4 meters per second. So I'm just looking at a system that has the ball and the earth in it. I'm not going to put the cat in it because I want to look at what the cat is doing, the force that the cat is applying as work on the ball. So initially, the ball is at rest on the ground. And at position B, the ball is moving at 4 meters per second. It's still on the ground. So initially there is no energy in this ball, but at the end there is kinetic energy because it is moving. We're just ignoring any friction here. Okay, so that energy that we see in the ball at position B has come from the work that the cat did on the ball. So in this case, the work equals the change in the kinetic energy of the ball. And so we want to calculate how much work the cat did on the ball. So that work is the change in the kinetic energy. And so that's going to be 1/2 the mass of the ball times the square of its velocity at position B. Let's see, I'm going to make sure before I plug in here that everything is in standard units. It's a 25-gram ball, so it's a 0.025 kilogram ball, and its velocity is 4 meters per second. I square that. And so the cat did 0.2 joules of work on that ball. Let's look at the next one. This next problem also concerns a ball. This is a soccer ball, but now we have a soccer player whose foot imparts a force of 250 newtons to this ball that has a mass of 0.3 kilograms. And her foot moves the ball a quarter of a meter. So we'd like to know what is the ball's speed immediately after it's kicked. So at the beginning, the ball is at rest on the ground. But after the soccer player kicks it, it's moving. We don't know how fast yet. So this is a very similar situation to the cat, playing with the ball. Again, we have a situation where there is no energy in the soccer ball at the beginning, but at the end, the soccer ball is moving, and so there's kinetic energy. The kinetic energy that we see in the ball at position B is there because the player did work on the ball by applying a force to the ball. So the conservation equation is the same as up above. The work that was done on the soccer ball equals the change in the ball's kinetic energy. But in this particular case, I don't have the information to calculate the energy, because even though I have the mass of the ball, I do not yet have the velocity of the ball. In fact, that's what I'm trying to solve for. So is there a way to find work other than by equating it to how much energy it has transferred? Yes, work is equal to the force that's applied multiplied by the displacement of the object. So here we know that the soccer player exerted a force of 250 newtons, and she caused the ball to move a quarter of a meter. Now the ball has a mass of 0.3 kilograms, and I'm looking for the velocity. So that's what I'm going to solve for. So the velocity of this ball is 20.412 meters per second. So I'm just going to go back and look at these two situations. In the first situation, we are inferring how much work was done by looking at how much energy was transferred into the system. And here, that energy was transferred in and was stored as kinetic energy. So in number 3, we found the work by calculating how much energy was transferred. In number 4, a similar situation, right, in the sense of our conservation equation looks the same. But here, we did, instead of inferring how much work was done by looking at how much energy was transferred, we calculated the work that was done by taking the external force that was applied and multiplying it by the displacement that it caused. Okay, so 2 ways that we can find work. Let's look at another example. So here we've got a piano that's being lifted 12 meters to a second floor window. I'm going to take my system just as the piano in the earth because I want to consider the work that is done on the piano. So at the beginning, the piano is at rest on the ground. And then when it has been lifted up 12 meters, so now it's 12 meters high, it's still at rest. It was moving as it was moving between the ground and 12 meters high, but when they get it up there, it's at rest. Okay, so we have no energy in the piano at the beginning at position A, and at position B, the piano has gravitational potential energy. And all of that energy that we see as gravitational potential energy at position B is there because work was done on the piano and transferred energy into it. So our conservation equation is that the work equals the change in the piano's gravitational potential energy. So in this case, I'm going to be able to infer what that work is by calculating the amount of energy that was transferred. Notice that this is different than in number 3. In number 3, the work was equal to the change in kinetic energy. Here, the work is equal to the change in gravitational potential energy. So work is just the transfer of energy. Energy is energy. So in different systems, work will, the energy that's transferred may be stored in different ways. But here I'm going to calculate that work because I can find the gravitational potential energy at position B. I know the mass of the piano is 150 kilograms, G is 9.8 meters per second squared, and it was moved to a height of 12 meters. Therefore, 17,640 joules of work were done on this piano. Let's go on down to number 7. I'd like to do one that involves more of a, maybe a slightly more complicated scenario. So here we have bobsledders pushing a sled with constant force. They make it was at rest initially. So at position A, the sled is at rest and it's on the ground. But they make the sled move, and so at position B, it's moving at 10 meters per second, and it's still on the ground. The height is not changing of this sled, okay? It says to ignore both friction and air resistance, and we want to know what force the team exerts on the sled, okay? So initially, I'm just going to take my system to be the sled and the earth. I'm leaving the bobsledders out of it because I want to consider the work that they are doing on the sled. And so I need them to be part of an external system. Okay. So initially, when I consider this system, the sled and the earth, since it's at rest and on the ground, it has no real internal energy. But at position B, it's moving at 10 meters per second, so it has kinetic energy. And the problem has told me to ignore friction and air resistance. Okay. So that kinetic energy that I see in this sled system at position B is there because work was done that transferred energy into the system. The work was done by the bobsledders applying the force on the sled. So the work here equals the change in the kinetic energy. So I have a decision to make here. Let's see, the question is, what force does the team exert on the sled? Well, the place I'm going to see that force is if I try to calculate the work as the force that's applied multiplied by the displacement that it causes. And the kinetic energy I could calculate as 1/2 the mass of the sled times its velocity squared. So here, the thing that I'm going to solve for is this force. And I think I have the other things that I need here. So it says that they applied a constant force as they moved the sled along a 50-meter track. So the displacement that this force caused was 50 meters. They gave me the mass of the sled as 235 kilograms. And at position B, it's moving at 10 meters per second. I want to square that. And so I can solve for that force. And I get 235 newtons.